This is section 4.2, the natural exponential function. And so the first thing we see is just that there is a base for an exponential function called e. And really the only thing you need to remember is that e is just a number. E is just a special number. It is an irrational number, which means, as you can see, it has this decimal behind the 2 that just keeps going forever and ever and ever and ever. It doesn't repeat. That's why it's an irrational number. But because it's so special, it has been labeled E. E is seen in nature, meaning it is seen naturally. And we'll see some cases of where it does occur naturally in a little bit. But just understand that it's a number between 2 and 3, and that the graph of E to the x looks very similar to the graph of 2 to the x. It's just a little bit steeper because the base is a little bit bigger. But other than that, it's just like anything we've already seen in terms of exponential functions. It's just so special that it is often called the exponential function. So what you'll find is with any scientific calculator, you should have the base e. So on the calculator that I recommend, you're going to find e. When's the last time I used that? Right above where it says ln. So you'll see a button that says ln. Above that, you'll see e to the x. And that's the button that we want to use anytime that we're going to be using this base e. So as you can see, the first couple things here just say evaluate and round answers to 3 decimal places, just trying to evaluate e. So with whatever scientific calculator I hope you have right now, what I'd like you to do is see if you can get the answers for both of those. So you're wanting to just use the exponent 5.4. So you're going to put the base e, put the exponent 5.4, and if you're rounding to 3 decimal places, you should get this. So if you didn't already do it, which I hoped you would, do make sure that you try at some point to make sure that you can get these answers. You don't want to get an answer wrong just because you've put it into your calculator wrong when you know what it actually, is. So as you can see, it arises in many applications. If you were to compound interest continuously, so literally every single second you're compounding interest, the base of that is e. So that's where it occurs naturally. We also see, if you've heard of exponential growth, exponential decay, those are also base e. And you have a growth rate or a decay rate, depending on whether you have a population that's growing or a population that is shrinking, essentially. So we'll take a look at just a couple examples of where we see E and how we can use it in the natural world here. So the number of bacteria in a petri dish after T hours is modeled by Q of T equals Q naught times E to the 0.05 T. If there are 100 bacteria present initially, how many are present after 1 day? Round answer to the nearest bacteria. So you can imagine that since we're talking about growing bacteria, we'll be using our Q of T equaling Q naught times E to the KT. So in this case, we want to be thinking about, do we have Q naught? Do we have K? Do we have T? So take a look at the problem. If you want, you can pause for just a very quick second and see if you can put any values there that you know and see what you get. All right, so we're told that we have 100 bacteria present initially. We're actually given, this whole thing. We're told that K is 0.05, the growth rate, so we already have that. The biggest thing here would be T. Do notice that it says T hours. That is what the model is giving us, and we want to know after 1 day. So we want to be a little bit careful there, because if we put T being 1, even though our formula is in hours, that's going to give us an incorrect answer. So if we were to put T equals 1 and we were to do the rest of this work, it's only going to tell us after 1 hour, and we want after 24 hours. So we're going to have Q of 24, and that will be our Q naught times E. So E, remember, E here is a number, so it's nothing that we're looking for. It's already there. And then we're raising that to the 0.05 times T times 24, like that. And then we just plug and chug. We go ahead and put that in the calculator and we see what we get. You can do that all in one shot if you want, and see what comes out. We will be rounding it to the nearest bacteria, so that just means the nearest whole number. So we'll have 332,0117, so that's about what we get there. So we'll have about, after 1 day, about 332 bacteria. Okay? So notice, I mean, that's going from 100 to 332 in just 1 day due to the growth rate and the fact that we're following exponential growth. Okay. So to put these in the calculator, I'm going to just show you how to do that in one step. So for the one about the Petri dish, we have 100 times, and then I need to find the E button, e to the x. So you can see that on Desmos, it's here. Notice it puts the E, it pops right into the exponent. E does need an exponent. If you don't put anything, it'll typically default to 1, e to the 1, but we don't have that. We have something else. I'm going to put parentheses. They might be necessary, they might not. It just depends on your calculator. This one would not require parentheses in my exponent, but I'm going to put them here. Put the 0.05 times 24. I can close it up if I want. And you'll notice over on the right-hand side, it's already giving me the answer that we got. So I don't really need to do much more. There it is, showing you how we put that in. And notice I put the application text box there again, just so that we can refer to it. Now we're being given money here. We're being given money. So because of that, we're going to be using this formula. You should notice they're very similar. It's just kind of using different letters for the different values that we are being given. So in this case, because we're using continuous compounding of interest, sometimes called PERT. If you notice, the right-hand side does actually spell PERT in a weird way. I mean, R and T are exponents, but just saying. In terms of finding out how much will be in the account after 5 years, we do want to look at what values we have. So go ahead and put whatever you're being given. You can pause if you want, fill in the values, P, R, and T. So we have 10,000, 0.015, and 5 years. Now, we just simply put those values in and see what comes out. E, and then we put our R always as a decimal, not as a percent, times 5. There we go. And we plug it in and we see what comes out. And you should have, hopefully, 10,778.84. Talking about money, so we're going to round to the nearest cent. So how much will be in the account after 5 years? After 5 years, there will be 10,778.84. Now you might think, hey, that's less than the one we did in the last section. But remember, that had a lot higher rate. The R on that was a lot bigger. So just remember that. Compounding continuously is actually the best thing that you can do. Your money will go like this. Just know that. But you're not really going to find continuous compounding very often. Most places compound, monthly, annually, biannually, something like that. Okay, so that's just a couple examples of E and using E, and then we'll continue to see E in all the rest of our sections. For the other one, very, very similar. We have 10,000 in that case. 1, 2, 3. And we're going to multiply that again by e. So we're going to grab our e function up in my exponent. In this case, looks like I'll have 0.015 as my decimal, so 0.015 times 5, and close it up. And again, over on the right-hand side, we're seeing exactly what we got, what I got anyway. And so that's how we can put it in one step and see our answer. Sometimes students do want to do these in pieces and like write out each piece, but I will say that can leave room for rounding error or just any kind of error that could occur. So once you've done the setup, it's pretty legit to just go ahead and put it in the calculator, write it out the setup so I know what's going in there, and then go ahead and put it in the calculator and see if you can get that most exact final answer. And that's section 4.2.